Alright guys, today we're going to learn about partial derivatives, a brief introduction to the basic concept of it. We'll start by considering the cost equation, 500 plus 70x. And recall from the previous lesson, x is the number of standard surfboards being produced weekly, and c of x is the total cost for that week. Let's start by finding c prime of x and determine the result. So c prime of x is 70, and this means that the weekly cost is increasing by $70 for 1 unit increase in production of the standard surfboard. Right. So we can also refer to this as the marginal cost as well, right? Suppose we look at the total cost equation for producing two types of boards, standard and competition model. Previously, we looked at this and we said, suppose we get the total cost equation that is 700 plus 70x and plus 100y, where x is the standard surfboards and y is the competition boards that produce weekly. Now, suppose we want to differentiate respect to x while holding y fixed. Okay, what does that mean? It means that the company decide to increase production in a standard surfboard, but keep the production for the competition model fixed, meaning no increasing, no decreasing. And what would that look like in terms of derivatives? Well, it turns out that itself is called a partial derivative, because with the function of several variables, there's more than one variable. So when we take the derivative with respect to one variable only, it's a part of that function derivative. So it's called partial derivative. So in this case, if we want to take the partial derivative of cxy 700 plus 70x plus 100y. Now, if we want to see how the cost is changing, so we want to see how the cost is changing. While x is changing, meaning the production in the standard surfboard is changing, keeping this variable constant, meaning the production is constant, not changing, isn't changing. All right, so that's what we want. We want to see the change in cost with respect to x, but not y. So when we do this derivative, we're gonna differentiate term by term. So we're gonna differentiate. So let's call this new partial derivative, call that c sub x of xy. Derivative of c with respect to x. And when we do this here, we're gonna say derivative of 700 is gonna be 0. Okay. Derivative of 70x with respect to x is 70. And the derivative of 100y, well, if we say the production of y is not changing, we say that the change in y is constant, then the derivative is 0. Okay, so we treat the y variable as a constant value. So our derivative here, our partial derivative, is just 70. Okay, so we say that the partial derivative, so we say that the partial derivative is 70, or c sub x xy is 70, is the change in cost in standard surfboard productions while keeping the production of the competition board constant. And so that's the interpretation of the partial derivative of c of xy is 70. Now let's practice that and let's calculate c sub y xy, and we're given that that's 100. So let's see, c of y, let's go back again. We know that c of xy is 700 plus 70x plus 100y. So when we calculate the partial derivative with respect to y, we differentiate term by term. So we say this is constant, so that's 0. And now we're not looking at the change in x. We assume x is not changing, so that's a constant as well. So that's going to be 0. So now we say y is changing, production in the competition surfboard is changing, so this is changing. Okay, or increasing, the production changing. So the derivative of 100y is just going to be 100. So therefore, c of sub yx is 100. Or the partial derivative with respect to y is 100. This means the changing cost in the competition surfboard is increasing by $100 per board, while we're keeping the production in the standard surfboard constant. Okay, so that's what it means. Now we're going to introduce the general notation for partial derivative. We can define a new variable z. If the function is f of xy, we can define the output call that letter z. Then we can say that the partial derivative with respect to x while holding y fixed is called the partial derivative with respect to x and denote as f sub x y and f sub y xy. So this is just more generalized way of defining or denote the partial derivative. Whereas up here is sort of introducing the concept of partial derivative through the total cost equation that we have built up since 7.1. In example 1 here, we also have another notation that denote the partial derivative, this Greek letter d here. So usually we do dy dx, that's the notation of derivative. With partial derivative, we use this delta, or this letter d in Greek here, denote as partial derivative. So when we do partial derivative of z with respect to y, this is saying that this is the same thing as saying that find the partial derivative of y, x comma y. Okay, and we're gonna differentiate these guys. Okay, so we're gonna keep y keep x. So we're gonna say treat x constant, assume x is constant, and differentiate respect to y. So we can say treat x as constant and differentiate y. Okay, so we're going to go through this term by term. We say, okay, 2x squared was now, okay, so we treat x as constant. So 2x squared is just a constant variable of value. So that's going to be 0. Okay, over here, if x is constant, this treat as the coefficient. So that's also a constant. So derivative of 3 minus 3x squared y, treating x as constant, and the derivative in this case using the power rule, this is going to be minus 3x squared, right? So kind of like, what's the derivative of 5y? Well, let's back up here. What's the derivative of 7y? Well, it's just going to be the coefficient 7. So think of 3x squared as a coefficient. So all right, next, derivative of 5y, again, we differentiate respect to y, so it's going to be 5, and derivative of 1 is going to be 0. So our partial derivative with respect to y of x and y is minus 3x squared plus 5. Okay. And part B, we're asking to evaluate that derivative at 2 and 3. So that means x equal to 2 and y equal to 3. We're going to plug that into the derivative. So that gives us minus 3, x is 2 squared plus 5. So that's minus 3 times 4 plus 5. Minus 12 plus 5 is 7. So that's going to be 7. So notice that this partial derivative with respect to y doesn't have the remaining y variable, and that's okay. So we only plug in the x in this case. Now I want to do another similar problem with respect to x in this case. So let's call this part C. Let's find the partial derivative with respect to x of xy. All right. So this means we're gonna treat y as constant and differentiate x only. Okay. So we can go through that function of several variables of 2x squared, 3x squared y plus 5y plus 1. We'll differentiate this with respect to x only. This means we're going to treat y as a constant variable. All right, so let's see here. We have, so differentiate derivative of 2x squared. So differentiate with respect to x. In that case, it's going to be 4x. And derivative of minus 3x squared y. So the y variable in this case is constant. So we're looking at minus 3yx squared, and this is a constant coefficient here. So when we apply the power rule, we get minus 6yx. 2 minus 1 is going to be 1 there. Okay. And the derivative in this case is of 5y is going to be 0 because we are treating y as constant. And 1 is also constant, so that's going to be 0. So our answer now is 4x minus 6yx. Right. So that's a partial derivative with respect to x. Okay. All right, so we have one more example. And this one is the e function. So e to the power of x squared plus y squared. This will require us to use the chain rule in this case. So part A, we want to find the partial derivative with respect to y. So this is the same thing as f sub y xy. Okay, and the function is this. So f sub y of xy is the partial derivative of this function here with respect to y. So that means, again, we're treat x as constant, differentiate y. Okay, so first we start by differentiating the e function. So anytime we differentiate the e function, it's equal to itself. So that's going to give us e to the x squared plus y squared. So that's the outside function. So now we apply the chain. We'll say, okay, the derivative of e to x squared plus y squared is e to the x squared plus y squared times the derivative of the inside functions. So the derivative of inside function is d dx, or in this case d dy. So in this case is d dy of this x squared plus y squared. X is constant, so that's going to be 0. So we're just going to differentiate y normally, so that's going to give us 2y. Okay, so now our answer here is 2y e to the x squared plus y squared. That is our f of y xy, the partial derivative with respect to y. All right. I think I had another example, but let's see here.